Today, I'm going to tell you about bridging time by bridging space. I'm going to tell you about how we can use what is currently a tremendous era of exploration to leave a legacy for future generations. So, to start off, I want to take us back to the old days, back before 1989. Those were the historical periods when all the planets that we knew about in the universe were the ones in our own solar system. There's the inner planets in our own solar system that you can see with the naked eye, and these were known to all ancient civilizations. And then, after the invention of the telescope, we finally were able to discover the planets in the outer solar system, Uranus and Neptune and then Pluto. Of course, we lost one on the way, but that's not the issue. However, since the early 1990s, there has been an explosion of discovery. If we were to plot the total number of planets that are known, then we would see a gradual increase over the centuries, followed by a huge explosion just in the past few years. There are now thousands of planets known, not in our own solar system, but orbiting other stars in our galaxy, in addition to the 8 planets in our own solar system. These discoveries represent a tremendous pushing outwards of boundaries of what we understand about our own lives and our own place in the universe. They also represent a tremendous change to how we knew that planets could be and could exist in relationship to their own stars. Before the discovery of all of these exoplanets, planets orbiting other stars, we expected most other solar systems would look somewhat like our own. However, we've discovered there's entirely new classes of planets that we don't have in our own solar system that are orbiting other stars. Some of these are big gas giant planets like Jupiter and Saturn. They're made out of hydrogen and helium gas, only instead of orbiting once every 10 or 20 or 30 years like the ones in our own solar system, they're orbiting once every 3 or 4 days, right next to their host stars, the so-called hot Jupiter planets. Some of the other planets have the mass of the Earth or Venus. They're basically big balls of rock and metal, like our own planet, except they're orbiting so close to their host stars, they orbit the stars once every 8 hours. In those cases, the surfaces of those planets are thousands of degrees. In fact, they're lava worlds. Their entire surfaces are molten rock. Other planets that we can observe, where we can measure their masses and radii, which allows us to determine the densities of these planets, and we can calculate their overall densities, do not have the densities of gas giants. They do not have the densities of a terrestrial planet made out of rock and metal like our own, but rather they have the densities of what we call ices. Things like ammonia, methane, carbon dioxide, and mostly water. These are water worlds, hundreds of miles deep of liquid water and methane and other ices around an inner core of rock and metal. And we've also found some planets that are so bizarre they don't orbit a single star, but they actually orbit double stars. You have a pair of stars orbiting each other very closely, and then another planet orbiting around them. Those are the circumbinary planets, also called Tatooines. There's really no way around that. But of all the discoveries, probably the most profound and fundamental for our understanding of ourselves is the discovery of planets that are in the so-called habitable zone. This is a term that's thrown around a lot casually, but what it really means is something very simple. It means that these are planets who are orbiting at the distance from their host stars, such that the temperatures of these planets would allow liquid water to exist. And liquid water, as far as we know, in terms of the life on our own planet, is the key ingredient that you need in order to have life. There are a handful of planets that have been discovered that are terrestrial type planets, basically like our own, that are in the habitable zones of their stars. This is a picture of some of them along with our own Earth. But these are all artists' renditions. These are all what artists imagine these planets would look like. Because none of these planets have been observed directly. All of these planets we know about through indirect discovery, primarily through the gravitational pull of the planets on their host stars, allowing us to determine the masses of those planets, along with the fact that some of these planets will eclipse their host stars, and in eclipsing they block some of the light from the star, causing the stars to dim a little bit. And that allows us to calculate the size of the planet. So when you have size and when you have mass, then you get density. And that allows us to determine that these are terrestrial type planets, like our own. And if they are orbiting at the right distance from their stars, they're in the habitable zone. But it's a little bit frustrating to think about this in the sense that we know about these planets. They're very exciting locations because we want to study them so much more to learn about their properties, but we can't see them directly. Furthermore, we want to try to understand their intrinsic properties. There's a quote from a philosopher back in the 1850s who was thinking about this idea and thinking about the problem of how you talk about and investigate planets around other stars that might be discovered. People have been thinking about this for hundreds of years. And his statement was, we see how we may determine their forms. He's talking about these other planets. Their forms, their distances, their bulk and their motions, but we can never know anything of their chemical or mineralogical structure, and much less that of organized beings living on their surfaces. Now, that was a very discouraging thought at the time, but at the time it was also absolutely true. There was no mechanism that anyone could think of for trying to understand what those planets were made out of, what their atmospheres were like, what their surfaces were like. But the great advance that happened was about 50 years after this, in the early 20th century, with the discovery in physics of quantum mechanics. And you might wonder what quantum mechanics has to do with the discovery of planets at astronomical distances. But what quantum mechanics allows you to do is to see the light that is emitted from some heated object or reflected off of some surface. And you can analyze the color of that light and break down the different wavelengths of light and determine what that thing is made out of. You can figure out the composition of the star who's shining towards you, and you can discover the material that is emitting light. So how do we use this to understand the properties of planets? Well, there's two main methods. One of them is called transmission spectroscopy. Let's take the example of one of these planets that eclipses in front of the face of its star, allowing us to see that sort of shadow move across the star. In that case, most of the light that we see when we look at that star when the planet is in eclipse is going to be coming to us directly from the star. A fraction of that light, maybe about 1% or less than 1%, will be blocked by the bulk of the planet. But a tiny, tiny fraction, maybe 1/1000th of 1% of the light from the star, is going to enter into the outer atmosphere of the planet and be absorbed and re-emitted along its path length as it travels through the atmosphere and then make its way to our telescope. We have a lot of very sophisticated techniques for disentangling the light from the star from the light that filters through the atmosphere. But when you analyze that light, you can break it down into its components and to the individual colors. And by doing so, you can detect through these processes the presence of materials in the atmosphere of the planet. You can detect things like methane, or ammonia, or sodium, or carbon dioxide, or even water. And we have done this for maybe a half a dozen planets, and we're working on doing this for hundreds more. But it's a very time-consuming and difficult process. There's another way of doing this called direct spectroscopy. And that's the case where instead of the planet going in front of the star, you can actually see the light directly coming from the planet. Now, this is a tremendously difficult thing, and that's because planets are extraordinarily dim compared to their host stars. The best case scenario that we have looks something like this. In this case, this is an image of a system called HR 8799. And in this case, you have planets that are orbiting this central object here. What we're seeing here is a case where the star is being observed, and we are blocking out 99.99999% of the light from the star. And in the midst of that blocked out light, we have this residual light that we can't block out, and then we can see the planets going around the star. But these are not just ordinary planets like our own. These are big gas giant planets that are very young, and so they're glowing from the heat of their formation, and they're also extremely distant from their host star. So these are the extreme planets that we can observe this way. What we want to be able to do is do this for planets like our own, but that will be a tiny little blip nestled into the middle of the light that's barely being blocked out. When we look at these kinds of planets here, we can take the light from that planet that's actually emitted from the surface of that planet and break it down and measure the presence of materials in that planet's atmosphere. But what we want to do is we want to zoom in really far into the inner structure. And if there happens to be a terrestrial type planet orbiting at the right distance where you could have liquid water on the surface, then we want to take that light and break it down and then see if we can actually measure the presence, not just of things like carbon dioxide or nitrogen or even oxygen, but specifically chemicals that would directly represent the emissions of living things. So in our atmosphere, molecular oxygen serves that purpose. The oxygen that we have in our atmosphere is produced by living things. And as far as we know, There is no natural chemical process that would allow us to create this much oxygen in our atmosphere through non-biological methods. Now, that's the kind of thing that we want to look for on other planets. Not necessarily oxygen specifically, but any other kind of material, any other kind of chemical constituent of the atmosphere that would be displaying what we call disequilibrium chemistry, the chemistry of living things that cannot arise naturally. That's what we want to do. But this is difficult. Ultimately, what we're trying to do is we want to look for extraterrestrial life. We want to look for a planet that's orbiting a star that's got a solid surface, an atmosphere, and a magnetic field that happens to be in the habitable zone. That's the goal. Now, we're not saying that this is what all life needs. We're saying that this is what life needs of the kind that we know of on our own planet. We're not saying that we're looking for any kind of life. We're trying to find life that's something like ours, because that's all we can do right now. That's the extent of our ability. So what we're starting off with is discovering planets. We've done that. We're then measuring the atmospheres with spectroscopy. That's in the process. Then what we want to do is directly image a habitable zone planet, to actually see the little light from the planet and break it down. But ultimately, what we want to do, and this is going to be done with a NASA mission called HabEx, which hopefully will fly sometime in the 2030s if Congress is willing to budget the money. But ultimately, what we want to do is to get a resolved image of a habitable zone planet. That's what we want. We want to be able to look and say there is a planet there with where we can see the surface, where we can see clouds and vegetation and coastlines. I don't know when that'll be done. It will require something like a formation of telescopes locked together in space, all combining light, looking at a single star. But it's very difficult. This is going to require something on the scale of the Apollo program. But it can't be relying on national security and Cold War rivalries. It's going to have to rely on our own desire to achieve fundamental understanding of our place in the universe. And this is what I want to leave you with. This needs to be the legacy of our civilization. We have an obligation, when we have the ability to understand something about our universe, to leave a legacy for future generations so that they can understand better than we. And I want to close with a quote from Carl Sagan. And this has to do with the picture that you see here. This picture is the last photograph taken by the Voyager spacecraft as it was leaving the outer parts of our solar system. It turned around and took one last picture of the planet Earth. That's us right there. This light here is refracted light from our sun refracting around the edge of the telescope lens. But there was something remarkable that was noticed about this by Carl Sagan. And I'm going to read you this quote. Look at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived here, on a mote of dust suspended in a sunbeam. We have the ability over the next few generations to build the kinds of instruments that will allow us to not be the only motes of dust and sunbeams, but to be able to point at other points of light in the sky and to say, there is a place like here. There is a planet that doesn't just show up as a dot on an image like this, but where you can actually see the signs of living things and possibly other civilizations. It's something that will take generations to accomplish, but I think it's worth it because I think this is the kind of thing that can inspire people to greatness. Thank you very much.